We often think we've got a pretty solid grasp on the fundamental forces around us. Take magnets,
Yeah, absolutely.
from like the ancient Greeks with lodestones to the ones on your fridge door holding up notes. They feel so familiar.
Totally. Part of everyday life.
But what if I told you that, well, for almost 100 years, science was actually missing a huge piece of the puzzle about magnetism?
Oh, interesting.
Yeah, what is a third kind of magnetism has just been discovered, challenging like everything we thought we knew.
Okay, I'm hooked.
Welcome to the deep dive. Today we're diving deep, really deep into altermagnets,
Yeah,
this third revolutionary type that's basically rewriting the science books.
that's right. And our mission today for you listening is to figure out, okay, what are these altermagnets? Why is finding them such a massive deal?
Right.
And crucially, how could they potentially change technology, especially computing as we know it? We're going to break down the latest stuff, the research, try and make it all clear and hopefully kind of exciting for you.
Okay, so let's start with the basics. For ages, humanity really only knew about two main kinds of magnetism. The first is the one we all think of, right? Ferromagnetism.
The classic magnet.
Exactly. Fridge magnets, compasses. Can you just quickly remind us how that works fundamentally? And then how did the second type, antiferromagnetism, sort of flip that idea?
Sure. So ferromagnetism, it's all about electrons. These tiny particles have this quantum thing called spin. Think up or down.
Okay.
When electrons aren't paired up, they give an atom a sort of magnetic nudge, a magnetic moment. In ferromagnets, enough of these atomic moments line up, all pointing the same way, like little arrows all aligned.
Got it. Like soldiers in formation.
Pretty much. And that creates a strong magnetic field you can feel, the kind that sticks to your fridge or pulls iron filings. It's this tiny spin property that's actually key to everything magnetic and, as we'll see, maybe key to new computers, too.
Okay, so that's type 1. What about type 2?
Right. Then in the 1930s, this physicist, Louis Néel, he theorized antiferromagnetism. Here, the atoms still have those magnetic moments, those little arrows,
Uh-huh.
but they point in opposite directions, alternating. Up, down, up, down.
So they cancel each other out.
Exactly. It's like a magnetic standoff. There's order at the atomic level, sure, but because they're opposing, there's no overall magnetism you can detect easily. Néel actually got a share of the Nobel Prize for that idea back in 1970.
Okay, so that was the picture for, what, almost a century? Two types. It seemed pretty complete.
Yeah, seemed like it.
But then, 2018, a PhD student in Prague, Libor Mikl, he's looking into this weird effect in antiferromagnets, the anomalous Hall effect.
Right, that's a subtle thing where electricity doesn't behave quite as expected in, well, what should be non-magnetic materials.
Exactly. And Mikl realized this effect and some other magnetic puzzles just didn't quite fit Neil's model. Something else was going on. He knew he had to look beyond the existing theory.
And this is where the story gets really wild, actually.
Yeah.
Mikhailov's inspiration, it came from art. Art? Seriously?
Yeah. M.C. Escher's Horseman print. You know, the one with the interlocking riders, shifting colors, that complex repeating symmetry.
Wow, okay. How did that connect?
Well, he saw that Escher's pattern used a kind of symmetry operation, flipping, shifting, changing color that could be described mathematically in a new way, going beyond the standard methods.
So he saw a different kind of pattern, not just in the art, but one he could apply to physics. Is that the idea?
Precisely. Symmetry is like the language of material science. It describes how atoms arrange themselves. Neil's model relies on certain symmetries.
Yeah.
But Metcalfe, using his Escher-inspired math, he extended Neil's model. He thought in 3D, crucially, and included non-magnetic atoms in the mix. This completely new angle, this different mathematical lens, led him to predict altermagnetism in 2022.
Okay, mind blown already. So we have ferromagnets, antiferromagnets, now this third type. Help us picture an altermagnet. What's the key difference at the atomic level?
Great question. Okay, picture those alternating up-down spins again, like an antiferromagnet.
Yeah.
But here's the twist. In an altermagnet, every other atom is also sort of rotated, typically by 90 degrees relative to its neighbor with the same spin direction. This rotation, which happens in specific crystal structures, maybe with non-magnetic atoms around, it lets a subtle magnetic effect kind of leak through.
So even though the ups and downs still cancel overall.
Exactly. No net magnetism overall, like an antiferromagnet. So they don't stick to your fridge. But, and this is the absolute key, they still have some of the useful quantum properties that ferromagnets have, the ones that are good for tech.
Like what properties?
Well, the properties that allow for things like spin manipulation. As Miskal said, everyone got really excited because it looked like these things combine the best bits of both ferromagnets and antiferromagnets.
The best of both worlds.
Yeah.
And this wasn't just a theory, right? It got confirmed.
It did. Pretty quickly, too. In 2024, Juraj Krempowski and his team in Switzerland looked at manganese telluride. They suspected it had the right crystal structure. They used special light beams, synchrotron radiation, to basically watch how electrons moved inside it. And guess what? The electron behavior perfectly matched the simulations for an altermagnet.
Wow.
And what's really cool, another researcher, Oliver Amin in Nottingham, actually got the first image of the magnetic structure in manganese telluride. His team even showed you could control these structures by heating and cooling the material in a magnetic field. Plus, and this is important for actually doing stuff with it, manganese telluride is a known material. Scientists already know how to make high-quality samples.
That's a huge advantage. No need to invent a whole new material from scratch.
Exactly. It speeds things up immensely.
Okay, so this brings us to the big question. Why is finding a new type of magnetism such a big deal for technology? What's the potential payoff here?
Right. So current computers fundamentally store information using electric charge. Think of it as charge or no charge, representing a 1 or a 0. It works incredibly well, obviously, but it has limits.
But there's this idea, spintronics.
Yeah.
Using the electron spin, the up or down, not just its charge.
Precisely. Spintronics is the dream. If you could use spin, theoretically, you could cram way more information into memory, make devices much faster, and use a lot less energy. It's like a potential revolution for computing.
Sounds amazing.
Mm-hmm.
What's the holdup?
Well, the big hurdle for spintronics has always been needing something called a spin-splitting effect. You need to be able to separate electrons based on their spin, up or down, into different energy levels or pathways.
Okay.
Anna Helens, one of Mikal's colleagues, has a nice analogy. Imagine a ballroom full of dancers. Normally, they're all mixed up, but with spin splitting, it's like the dancers spinning clockwise can separate from the dancers spinning counterclockwise and dance in their own groups.
Ah, I see. You need that separation to work with the spins individually.
Exactly. And the problem was this crucial spin splitting effect. We really only found it reliably in ferromagnets.
Okay, but what's wrong with using ferromagnets then?
Ah, here's the rub. Ferromagnets have that strong magnetic field, remember?
Right, the sticking to the fridge part.
Yeah. So if you try to pack lots of tiny ferromagnetic components onto a computer chip really close together, they interfere with each other, they attract or repel their neighbors. This creates a physical limit, a ceiling, on how small and dense you can make spintronic devices. They basically start fighting each other.
Ah, so you can't shrink them down enough because their own magnetism gets in the way?
You got it. And this is where altermagnets could be the game changer. A physicist named Igor Mezim pointed out their unique combo. No net magnetism, so they don't interfere with neighbors. But they still have those spin-split energy bands. They still do the crucial thing needed for spintronics. They give you the spin separation without the magnetic interference problem.
Whoa. Okay, that does sound revolutionary. So Misko's quote about having all the functionalities but faster, smaller, less energy, that's based on this idea.
That's exactly the potential. It opens the door to potentially overcoming that density limit that plagued ferromagnet-based spintronics.
Yeah.
But are there hurdles? Absolutely.
Yeah, I was going to ask, it sounds amazing, but what are the challenges? Like actually making these things work in devices? Stability, manufacturing.
All valid points. Researchers are definitely working on it. One approach is kind of forcing the issue. They're trying clever tricks like physically squeezing known antiferromagnets.
Squeezing them.
Yeah, applying mechanical strain. The idea is to deform the crystal structure just enough to change its internal magnetic symmetry and maybe coax it into becoming altermagnetic. Atassi Chakraborty's group did this with rhenium dioxide recently, showed compressive strain could trigger it.
Huh. Clever.
Another trick being tried in Beijing is stacking antiferromagnets between other materials. This creates electric fields inside that might mimic the kind of atomic environment where altermagnetism naturally occurs.
So they're trying to engineer the effect. But are these scalable? Like for mass production?
Probably not easily, no. These are more like proof-of-concept lab experiments right now. Really cool science, but maybe not the path to your next smartphone chip just yet.
Right. So what's more promising?
Finding naturally occurring altermagnets seems like the better bet for practical uses. Amejel and his team have been running computer simulations, scanning databases of known materials. They've identified at least 200 potential candidates, Besides manganese telluride, which is now confirmed, there's strong evidence for another one called ruthenium dioxide. And having manganese telluride already confirmed is huge, like we said, because labs already know how to grow it well. That's a massive head start.
200 candidates. That's a lot to investigate.
It is. It suggests altermagnetism might not be super rare, just overlooked. We didn't know what to look for mathematically until now.
And just when you think, okay, 3 types of magnetism, that's enough.
Yeah.
Humayskull throws another curveball.
You read my mind. He's even predicted a 4th kind, anti-altermagnetism.
Oh, my God. What now?
Okay, picture this. Instead of just up-down or up-down with rotation, the spins alternate in zigzags, like pointing northwest, then northeast, then southeast, then southwest.
Seriously. Zigzags.
Yep. These patterns form mirror images that, again, cancel out any net magnetism overall. But, crucially, this weird zigzag pattern also messes with how electrons move in just the right way to cause spin splitting.
So another way to get this contronic benefit without the ferromagnetic interference.
Potentially, yes. It just shows how incredibly complex and beautiful these symmetries can be at the quantum level. Things we haven't even imagined might still be hiding there.
Well, okay. So let's try and wrap this up for everyone listening. What's the big takeaway here?
Well, I mean...
We've just taken this deep dive into, well, a fundamentally new piece of physics, right? It changes how we even think about magnetism, a force we thought we knew inside out.
Definitely.
And maybe more importantly, it cracks open this door to potentially revolutionary technology, faster computers, smaller devices, less energy use. That's huge. I know for me, just the idea that Escher's art could spark a physics breakthrough.
Right.
Or that this weird magnetic stalemate could be the secret to better computers. Those were real aha moments in this deep dive.
Absolutely. And it goes back to what Heminghouse said about Escher's art, doesn't it? The more you look, the more delightful details you notice. Maybe the universe is like that. Maybe the biggest discoveries are still just hiding in plain sight, waiting for us to look with fresh eyes.
A great thought to end on. Keep that curiosity alive, because who knows what else is out there.
Exactly.
So if you found this deep dive as fascinating as we did, well, imagine what else we could get into. Please do like this deep dive, subscribe to the channel so you don't miss out. And hey, if you want to support what we do, check out the affiliate links down in the description.
Yeah, we'd appreciate that.
And we genuinely love hearing from you. Got ideas for other topics, mysteries you want us to tackle? Let us know in the comments below.
Please do.
Thank you so much for joining us on this journey into, well, a whole new magnetic world. Stay curious, everyone, and we'll catch you on the next deep dive.